Hello everyone and welcome to our calculus notes for section 3.7. Today we're going to be talking about optimization. And optimization is the process of determining minimum or maximum values in an applied problem. So in other words, we're talking word problems today. In order to do this, we're going to have to find a primary equation. And this is a general formula for the quantity to be optimized. So what do we want the maximum or minimum of? Is there an equation that will give us that value? Next, we're going to have to use a secondary equation. This is a specific equation to the problem used to rewrite the primary equation as a function of one variable. And then we also need to know about the feasible domain of a function. So just because the primary equation might be a function, it may not work for a feasibility of our word problem. So we need to find the values of x that make sense in the context of the problem. So here are some steps for solving your optimization problems. First thing you want to do is identify all given quantities and all quantities to be determined. And if possible, you're going to make a sketch. Okay? Next, you want to write a primary equation for the quantity that is to be maximized or minimized. Next, you want to reduce the primary equation to having a single independent variable. So that's going to be very important. So it's a function in one variable, and it may involve the use of a secondary equation here relating the independent variables of the primary equation. Next, you want to determine the feasible domain of the primary equation. That is, basically determine the values for which the stated problem makes sense, and then finally determine the desired maximum or minimum value using calculus techniques. So when you get your primary equation, basically you're going to want to take the derivative of that primary equation. That's why we want it as a function in one variable, so that you don't have implicit differentiation. And so that secondary equation is going to come from the problem, and there's going to be some sort of constraint given in the problem. Okay, usually as a known value. Now the calculus techniques that you're going to use here could be the first derivative test, most likely. Because that can find a max or a min on an interval. So here we go. A manufacturer wants to design an open box having a square base and a surface area of 108 inches. What dimensions will produce a box with the maximum volume? So a couple things here. We were looking for maximum. We're also looking for volume. We have an open box with a square base and then a surface area of 108 inches. So if we were to draw a sketch here, we would make a square base. We'll make it look all pretty here. And then it needs to be an open box. So our sides are going to go straight up here. You're actually getting a rectangular prism. And then we're not going to draw the actual lid on this box. So we're going to have to think about it as there's no top there. And so what I'm going to do is I'm going to erase parts that wouldn't be visible if the side of that box were there. Give it a little three-dimensional effect. Okay, so here we have this open box. Could be like an origami box. And it has a square base. So what that tells me is that these two values right here have to be the same. And so I'm just going to let the be x and x. And we also know it has a surface area of 108 square inches. So that right there is going to be our constraint when we get there. And we're looking for the dimensions that will produce the maximum volume. And this right here is going to give me my primary equation. Okay, so my primary equation is going to be the volume of this box. Well, it's just a rectangular prism, so volume is the area of the base, which is x squared, times the height of the prism. So I'm just going to label that h right there. Now the problem with this primary equation is we have too many variables. We want volume to be written just as a function of x. Okay, so what that means is we're going to have to come up with some sort of secondary equation That's going to help us rewrite this as a function of x. So the secondary equation is going to come from our constraint that the surface area has to be 108 square inches. Okay, so what we really need to do is write this in terms of h. But let's find the surface area of this box. So we know the surface area is going to equal all the areas of all the rectangles here. So we have the base, which is just x squared. And then we also have each one of these sides of the box, and that's just going to be x times h, and we have 4 of those guys, so we have 4x times h. Okay. Now our goal here is to go ahead and get h by itself and realize that this equals 108 square inches. Okay, so let's manipulate our secondary equation, solve for h. So we got x squared plus 4xh equals 108. We're going to solve for h. So we can see it's going to be 108 minus the x squared. Okay, and this is going to be divided by 4x. Now what we need to do is take this h and substitute it into our primary equation. So our primary equation here is going to be the volume equals x squared times h, which is 108, minus x squared over 4x. And because we want to take the derivative of this, we want to simplify this so that we don't get product rule, quotient rule. So we have the volume here is going to equal 108 x squared minus x to the 4th over 4x. And one trick we can do is actually divide each of these by 4x. So we're going to divide here 108x squared over 4x, which gives me 27x. And then negative x to the 4th over 4x, which is going to be minus x cubed over 4. Okay, so next thing we want to do is actually find the derivative of our volume. So dv over dx. And what this is going to tell me is how does the volume change as x changes. Okay, so derivative of 27x is just 27. And then the derivative of negative x cubed over 4 is negative 3x squared over 4. Okay, now in order to find our max and min, now we're going to use our first derivative test. And so basically we have to find our critical numbers by setting this equal to 0 and also finding where it doesn't exist. So because this is just a polynomial, it exists on the entire real number line. So where does this equal 0? Well, we're going to have to subtract 27 and then multiply by negative 4/3. So if we do that, negative 27 times 4/3 is 36. And then we'll take the square root and we get x equals plus or minus 6. Now here is where the word problem part comes in. Can negative 6 happen for x? No, that doesn't make sense. So we're just going to use x equals 6 as our critical number. Alright, next we're going to have to determine, is 6 where this is the maximum value? Okay, so we need to find our feasible domain here. And the domain, okay, x can go down all the way to 0, right? We can let this be really small and make a really tall box. So h could be really tall and x could go down to 0. So we know that x has to be greater than 0. And then there's also going to be a point where x could be too big and giving us a surface area that would be bigger than 108 square inches. So when we look at this, if we try to make x as big as it can get, and let's just say that this square bottom takes up the entire surface area. So if the entire bottom was 108 square inches, x would be square root of 108 times the square root of 108. And so we know that the square root of 108 has to be our highest x value here in the domain. Okay, so now let's go ahead and try our first derivative test with our critical number at 6. And so that means we have our intervals 0 to 6 to try out. And then we also have our interval 6 to the square root of 108. Okay, so now we're going to find our sign of our derivative in the interval 0 to 6, and then also in the interval 6 to the square root of 108. So here we could just plug in something like 1 into our derivative, and we get 27 minus 3/4, and so that is going to be positive. So we could try something bigger than 6 and less than the square root of 108. Well, the square root of 100 is 10, so let's try 10 here. 10 squared is 100 times 3 is 300 divided by 4. That's definitely bigger than 27, so this is going to be a negative number. So if our function is increasing and then it switches to decreasing, that means that this is a maximum here at x equals 6. Now we can find what the actual volume is by substituting it back into our volume equation, which is right here. I'll just do that right here. So volume is 27 times 6 minus 6 cubed over 4. And we actually get a volume here of 108 cubic inches. So the maximum happens here at 6,108. Now the question was, what dimensions will produce a box with this maximum value? So now we need to come up with our actual dimensions of the box. Now we know x equals 6, so that means we had 6 here and 6 here. So we know it's a 6 by 6 by, well, what's the height? Well, to find the height, we actually have to come back to our secondary equation right here of 108 minus x squared over 4x. So let's do that right here. H equals 108 minus 6 squared over 4 times 6, and we get a height of 3. So the dimensions of the box are 6 by 6 by 3. So let's just go ahead and go through and review what we did here. So we read our question, we came up with our diagram. Okay, the biggest thing was an open box with a square base. Then we came up with a primary equation for the value we wanted to maximize, which was maximum volume. And because it had an h in it, we want this all in terms of x. So we had to come up with a secondary equation here. And that secondary equation came from our constraint of a surface area of 108 inches. So we had to come up with a formula for our surface area. Then we had to rewrite our primary equation by solving the secondary equation for h and then substituting it in. And so this is our actual primary equation here, which notice we reduced down. And then what we did is found the derivative to try to find our critical numbers. So we set it equal to 0, and then we found our critical numbers. Okay, so that's another important step. Next, we looked at our domain just to make sure that this critical number was in the domain, and we also talked about our endpoints. So if we had 0, then we'd have a volume of 0, and if we had square root of 108, we'd have a volume of 0 as well. So we knew that those could not be our maximums. Then what we did is we went ahead and did the first derivative test right here. So we checked the sign of the derivative to the left and the right, and we did find that it was a maximum. Just for fun, we found the volume by plugging in our x into the primary equation. And then we had to find the dimensions to actually answer the question. And so to do that, we had to go back through and find our secondary equation, and we found the height right here. And so our dimensions were 6 by 6 by 3. So through this process, it's going to be very important that you write out all the equations, that you label them, primary equation, secondary equation, and you kind of label what you're doing in each step so that we can go back through and see the work that was happening here.